Okay, thank you very much for the invitation to be here. It's an interesting conference. I haven't been working on this problem for a long time, but I have been following quite closely. Before I start, I want to thank Maria. She's back there. We are officially organizers, but she did all the work, so this wouldn't happen without her. So thank you very much for all you have done for it, okay? So let's talk a little bit. People talked about Markov theory, but let's try to put this sort of the simple person approach to Markov theory. And the idea is that when you try to tunnel between two states, a state starts from a donor when you have an electron localized here. You go to a final state where you have an electron localized to the other state. So you have two electronic states. Like was discussed here, and Judy talked a little bit, these states tend to be completely off resonance. So you have to have nuclear motion to bring these states into resonance. That's what's responsible for the Frank-Condon factor, or the part that's Markov theory. Then here is, in the limit that you have electron tunneling a long distance, you have a matrix element that do it. On the conventional Markov theory, it didn't exist. When people just did chemical systems, it was just a question of bringing these two states in resonance, and the electron tunnel very fast. That was adiabatic. Actually, for more than I love Rudy, he's not the one who introduced this term. You have people like Yortner, Hopfield, many other people that brought these things. Now it's all called Markov theory. So when people talk about tunneling into these systems, there's always a question about two possible tunnels. One is clearly this that I'm going to talk most of the time. That's the matrix element for the electron. But there's the question about the nuclear part. And Judy will speak later. She's the expert about nuclear tunneling. She'll tell you everything from proton, from other systems. But it's a very interesting system, a completely different system. And these two things get coupled, the nuclear part and the electronic part, and people get very confused. Like sometimes people forget that when you show these parabolas on Markov theory, they're actually nuclear modes. In most of the cases, to simplify, you can imagine that's the polarization of the medium. And that's the polarization when the electron is on the donor. And that's the polarization when the electron is on the acceptor. So it's a completely different coordinates, the nuclear coordinate from the other one. On the old days, basically, this Hamiltonian, by the way, in physics, we work on it for a long time. It's a beautiful model. And this is the case when you use this sort of spin boson Hamiltonian. It was very popular by Tony Leggett and all these people in the past about talking about quantum coherence, decoherence. You can actually solve this problem. You notice it's a spin system that's just like your electronic state, coupled back and forth. You just use this notation by say spin 1 is donor, spin minus 1 is the acceptor.
I have a question, though.
Yes.
The very first slide. So why is the system not in the ground state, which is a symmetric wave function?
Because the polarization of the system is completely different, basically. When the electron is on the left, on the right, they are completely different environments.
Which is an excited state, though.
No, it's not an excited state. It's just the electron.
No, the ground state is a symmetric wave function.
First of all, the ground state wouldn't be symmetric because the state is not symmetric. Right, but the system starts because it's not an equilibrium state. We start by creating an electron. Most experiments, you throw an electron, it's not an eigenstate. You only start from one eigenstate. You start by putting an electron. If you wait long enough, they could do there, but then you have all this relaxation. So this Hamiltonian, but just for curiosity, has been done, a lot of work being done on it. The trouble with it is we can solve this problem exactly here. But if you notice our best is harmonic. That means the only way you're going to destroy coherence is by energy relaxation. So you're not going to get the full picture of the coherence into the system. Also, it's a system you can solve. In the case of overdamped limit, you can ever do the limit going complete from adiabatic to non-adiabatic. The weak coupling and strong coupling you can solve. So there's a lot of physics being done on here. But remember, we missed the fact that basically what we call T2 and T1 here, they're about the same when you're talking about on a harmonic best. But that's where the theory is. This problem was addressed in '74. I love this plot by John Hopfield. It's a very interesting plot. This is the reaction where the cytochrome put an electron into the dimer for photosynthesis. And what's beauty about this reaction is that if you believe on this data, if you believe on this experiment, that's the Walton chance experiment, is that you have to have an underdamped mode of about 250 wave numbers for this to be true. And that has been actually a major question in biology, if you really have this mode. So maybe you don't, basically, quantum mechanics here just starts to happen below 200 Kelvin to the effect to be great. So you may say it's not biologically relevant, but it's interesting the question that if you have this mode. The complication of this problem on this experiment, I just want to point this out, is that these modes may change a lot with temperature in biology. as you start to freeze water, you start to do that. So these extrapolations from high to low temperature, they are very dangerous game to believe that a mold that you observe at very low temperatures is the same mold that you observe at a high temperature, and that has been a nightmare in terms of this of the quantum mechanics of these nuclear molds. Anyway, we got into this problem in a completely different way. We didn't worry too much about the nuclear part, but we were interested, going in the wrong direction. We were interested on the problem of tunneling through the medium. And I'm going to sort of destroy Dave's talk because we did this work together. It means that he has to put some new slides to compensate for the fact I went before he did. But at that time we got it, people were very interested if the electrons could tunnel distance between 20 to 40 angstrom in proteins, if that was a tunneling process. So this is a resolved question these days, but it was a major question. Was that really a tunneling effect that you could go this distance 20 to 40 angstrom? Dave, on his new work, you can go much longer by this mechanism, but these were major questions. And the questions we had is how the electron interact with the bridge. And just to sort of put the back of the story before the early of the story, we figured out that this tunneling mechanism was actually what we call hole tunneling, that most of these electrons, when they tunnel in biology, they interact with the bound states, right? Much more than interact with the valence states of the system. And that gives equivalent of barrier of about a couple electron volts. If you had to go all the way up to the continuum or to the excited state, this barrier would be 5 electron volts. That we call this through-space tunneling. So there's this difference that if you go through the boundless, you are talking about the barriers of the order of 2 electron volts versus a barrier of 5 electron volts. That changed the entire physics of the problem, and that's where we got the situation. So what do we do? Basically, Dave was actually a hard worker, but he was a lazy Brazilian. So we said, how can we do this problem on the easiest possible approach we can do to that? And we say we are trying to compute these things. That's basically compute this green function that couple this donor and acceptor. And we can imagine if these things is decay exponentially, you're going to have a decay factor. That's the green function between the two terms. If it is a continuous bridge, this number should be the same for every bond. If it's different, they should be different, but this is very simple to calculate. But what we said is, how about if we say that decay factor for every bond is just a term? So we're going to approximate this wave function as being a product of decays and not have to do all this calculation all the time and say how much that works. That means we are neglecting backscattering and all these other effects, but we assume this decay is large enough that we can get away with this approximation. So the systems we're looking at, we'll be talking a little bit about it, are proteins. People experimentally learn how to put acceptors all around the surface of the protein by putting ruthenium bound there. Became great experiments that Harry Gray did, and other people, other groups started to do that. We could start to measure this electron tunneling. So, but the question we have again is says the protein is near the periodic backbone. We can say decay per bonds is a single number. That's about 2 electron volts. The decay through space, if you have to actually jump through space, a space that has nothing, is about 5 electron volts. So they're much more costful than going through the bonds. That the system means the wave function will try to follow a bond pathway as much as it can, only do a through-space jump if you have no other option. So that was the approximation we did on those days. And we put the decay per spect. This experiment, like I told you, you have here where people could transfer an electron from this heme to all this surface, and Harry Gray could put this histidine where they bound ruthenium, and you had all these acceptors on the surface, so you could probe direct coupling, direct through bond, direct when you have to jump through the pathways. You got a great system to go after that. The numbers we came to are very simple parameters, and that became magic parameters because now you could probe the entire protein and just look for the shortest path and try to couple. Now, so we said every bond's about 0.6. We say a hydrogen bond. If you forget this term, that's just a correction. Since you go through a bond and a lone pair is like 2 bonds for the counting. And the free space, the number that is the costful one. And you don't want to do that unless you have to. Now, so the problem now becomes on maximizing this number. Now, there's a problem here, and I will try to address that later. We are trying to say completely destroy quantum mechanics. Because the protein has all these possible pathways going around. All these pathways should be interfering with each other. You have all these complicated things we're talking about, and we cavalierly here say there's one dominant path, and that result gives us a great result. The beauty of it, and I'll come back to it, that's basically the punchline of what I'm going to try to come to this on quantum mechanics, is that first of all, biology, coherence is a tough thing for you. It's very non-robust. That's what I'm trying to say. So if you come towards biology and you try to think when quantum mechanics is important, you have to be very careful not to talk about coherent effects because they're very hard to survive for a long time and they're very non-robust. And so becomes a big problem when people start talking about these things, right? Particularly when you observe these states, how they live. So why these calculations that we did on the past, for our surprise, work much better than detailed quantum mechanical calculation of this matrix element? We could agree with experiments using these very simple calculations much better than anything else. So to have an idea, there are many systems that appeared out there. These are sort of several proteins that Harry Gray work, and we work with a combination of them. And we learn a bunch of stuff out of these systems. One of the curious stuff we learned, here's just experiments, just to show you how people did. They had these heme or copper atoms that were donors. Then you put a ruthenium here. You take a charge out of this ruthenium. You open a space here by you open a hole, and now you can measure the electron transfer. Okay, and then you can start the process again. So there was a way of measuring the electron transfer proteins in a very well-defined way. You could measure this rate. Now, the interesting result that comes is, this was the simplest result, came on a paper it came experimentally, but we had these predictions before the experiments were done, a paper we had in Science that tells you, as expected, if you decay through an alpha helix, directly through an alpha helix, you have a decay that's faster than a decay you do through a beta sheet. And that's kind of interesting, because to cover the same distance on a beta sheet, you have less bonds than you have on an alpha helix. And that's actually project on the numbers. This number 1.4 actually was a number that people have used on photosynthesis for a long time as being the decay time. But it's very interesting that on very careful experiments, you could notice this major difference on decay. There was something to really support that the distance is how many bonds you have to cover, more than just the physical distance we had. It became sort of one of the landmarks of the theory coming together. There are things based on decay through vacuum. Experiment is a big number. And then, like I said, water is sort of a disordered system of bonds, and it's a number in between. Now, this is sort of the data, and you can see the different decays. And it's actually very convincing if you look at the difference of all the systems and where the experimental date falls. Right, to see that basically nothing goes really through space, and you can see the difference with the beta strands versus the alpha helical proteins and all the dates come in place. Now, this is sort of one of the landmark things, because we went through a system where you try to really figure out now not just the through bond decay, like I told you, between alpha helix and beta strands, but a system where we really have to do a through space transfer. And we very carefully, on this case, studied the entire cover of this was a cyclone C and tried to figure out a system that, for example, we could find what we call He72, that somehow has a big void in between. So if it has to go through bond, it has to go a really long way around it. So the best pathway has actually a jump through space. And the beauty about this experiment is the electron transfer He72 is 1/3 of the electron transfer He39. Even so, the distance here is much shorter. So here's a case where the pathway prediction was an effective way of doing that prediction. And we did this thing. So at this point, we're very happy about these things. The model works. But how about the fact that I have neglected all this quantum mechanics? So I'm going to show a few papers that came afterwards that I think bring this issue, and it's become a big issue on tunneling these days, is what happens with all this other effect of incoherence. So we got some effects with people doing really quantum chemistry and stuff like that. First, the work I've done with Ilya Balabin was a graduate student at the time, and then work we did with Kim Baldridge and Shigusa Kobayashi as a postdoc, where we did the full quantum chemistry calculations in details of these matrix elements, put the full quantum mechanics, and try to compare to our pathway analysis. Again, we are computing the same thing, but now we are doing with better chemistry. The first system I'll talk is about the photosynthetic reaction center. So here we're going to notice systems where electron transfer is important. Biology requires to have fast electron transfer, otherwise they don't work. And that's the charge separation in photosynthesis. That has to be a fast event. You have no choice. That has to be quantum mechanically controlled. There is no way. When you do a full calculation from this field phyton to the quinone A, there are two very interesting things about the system. The dark, compared to the light gray here, is that people have measured this structure with the crystal structure in a normal condition, and the other, the crystal structure under light, to see if there's any structural change. On this first reaction here that you observed, you have no structural change to first approximation. And if you look at your main pathways, you start with your fight, you go through these through bonds, then you have this sort of two sort of space jumps here, they're basically, and you go to the field fight. But these things tend to be very rigid. They oscillate very rigid. So what we compare here is to see how coherent is the system here. And we have what we call a coherence parameter. And our coherence parameter is we run molecular dynamics into the system, like Jude is calling like noise. Let's call dynamics the protein, use the name you want. And we compute now what? We compute a term that's the square of the average of the matrix element over the average of the square of the matrix element. So it means that if this matrix element is changing sign too much, that term goes to 0. If changes very little, then the two terms are about. And you see this is a very, very coherent system. Okay? And that tells you that although you have two pathways, they just help each other a little bit. You're picking up a factor of 2 or 3 here, but you're not picking up too much. And what you observe is that the rates that we're computing here, both by pathways and by quantum chemistry, agree to each other. Basically, here's the number using the proper Frank-Cohn factor, typical number. We compute a number about 10 to the 11th. Second to minus 1. The experimental rate is 10 to the 10th. So we're very happy. Here is a case where you go around, you have two paths, but they're really incoherent, they're really coherent, they're really helping each other, they're not fighting each other. But now I switch the system just because it's very interesting. I go to a system that's the transfer between the two quinons. One electron has to transfer quinon A to quinon B. That's the end of the reaction. Here, quantum mechanics is not important. Electron transfer has to be slow. Biology has no reason to optimize it. First, what you observe is that the quinon has a big change from the dark form to the light form QB. That means you have a gating mechanism that's actually a slow event that controls these things. You have to switch that from one form to the other. And what you observe here is, here's the light mechanism, but what you compare here is to observe two things here. I won't go over all the numbers. What typical energy you have here, you observe that the rate, if you use the crystal structure, is about 10 to the 3. The experimental rate is 10 to the 2, 10 to the 3. The experimental rate is 10 to the 4, much bigger. If you do the average structure, it's even worse, it's 10 to the 1. So it tells you that here, these structures are nothing. If you do the average of these structures, what tells me there's a lot of destructive interference here. These things are just shaking around. Actually, if you do the real calculation, when you actually look for the states that are more, do good resonance, you get a factor 10 to the 6. That's more close to 10 to the 4. You have the gating mechanism that is low. So here's a case we have a lot of destructive interference, and pathways will give you about 10 to the 10th, because the distance is the same. So it tells you here is a case where pathway wouldn't give the answer, because you have multiple pathways, but that's not a system that quantum mechanics you have to optimize. Okay, so that's what you observe here. The system you have to do that. And we have a system with very few pathways. We went to the experimental system of Harry to have a look and tell you how dangerous to do these calculations. So just a few slides because I don't want to spend more time. Here is a calculation we did on Azurine, where people are electron transfer this copper site, and I think they're looking around this 122, 126 acceptors. So you're doing this calculation here. What you observe here is you have a direct path just going through here. And now you compute this matrix element at this point. What you observe here is this is time. So here I'm getting two particular inst of times. One that is basically, you have a maximum on this matrix element. Another one where you have a minimum on this matrix element. You just look at the decay for all the distance. And observe there's a big fluctuation here. So if you do a calculation here, you have to be very careful, because actually, when you compute the dA square, you're really dominated by the stuff here on the top. So even so, you may have some situations where these things shake around, and they give you and destroy your matrix element. That's not what dominates the tunneling. the tunneling is really dominated by these events up here. So you have to be very careful of not getting one structure and computing these elements. So the fact that you're dominated by, you may have some destructive interference down here, but this is going to count very little. That's why pathways survive. People say about noise helping you. It's not really noise helping you. Noise, basically, I think there was Julie comment about it, so did Thornton. These states can make the states shake enough of these situations to be on situations where you have a few paths dominating and quantum mechanics dominate, and that's why pathways survive. And I have another example here when we put the calculation crossing this system. Here you can see you can cross in many different ways. I'm just showing one of them. And again, these things fluctuate by a lot. But actually, if you just compute the effective matrix element, it's dominated by these things that are up on these states. And when you're up on these dominant values, then you're dominated by a single dominant pathway or by a few pathways that have exactly coherent interference helping them. And that's why, in the end, that simple calculation helps you a long time to do these things. So with that, we felt very comfortable. Why pathways survive, why these things coupled to experiments, why you have these very simplified models. But the most important thing, I want to go back to these things in biology. These things operate well when you have this fast electron transfer, when you're required to have a fast electron transfer. If you have situations where biologists are required to do that, even so in principle, could optimize the rate of electron transfer, in the case between QA and QB, you don't do it. You have no reason at that point to do that thing. The system is already up there. It can take its time, right? So you have a situation you come. So that comes back to this idea to biology that basically when this biology needs quantum mechanics. And I think I have 1 minute left here, do I? No, I'm not. I'm out of time. But when biology needs quantum mechanics, come on the idea that based on this is really required. So we know that electron transfer photosynthesis is required. We know the vision is required. Maybe on magnetism is required. But in other cases, I think the idea of nuclear tunneling, I'm going to let Jude to talk about, is very interesting. Is that necessary or that's in there for a situation? It's a very interesting topic of conversation, particularly in proton transfer, when you have classical and quantum proton transfer. I think it's a very interesting question, but guess the situation, when you need, you're going to use it, but if you don't need, I don't believe that you just do it for the sake of it. Okay, thank you.
Okay, we'll take some questions now, and then after David's talk, and then we'll have a more general discussion. So, yes, please.
Can you say again how you define coherence in the plot you showed?
Oh, in coherence, our definition of coherence is just we compute the matrix element each step.
Of what?
We do a dynamics calculation. We do a dynamical calculation, get the configurations on every time step, and you compute the matrix element on each time step. Then with our coherence factor is the average of the matrix element squared divided by the square of the matrix element. So in a sense, if you fluctuate very little, these two terms are the same. But if they start to have a long fluctuation up and down on the TDA, it means that you have these pathways change all the time. That thing goes to be a very small number.
So you're talking about coherence in between pathways, electronic pathways.
Exactly.
So I heard Tommy Miller recently from Caltech talk at our colloquium, our PChem colloquium, on azurin, on the ruthenium substituted azurin. And he was looking at an internal hydrogen bonded portion of the pathway. And they made mutants. And then he tried to reproduce the data in the wild type and the mutants. And his conclusion, I'm sure it's a recent paper in PNAS. I don't know if you've seen it or not. You've seen it. So his conclusion was actually that you had to have a large isomerization from the ground state structure that you see from the crystallography of about 2 angstroms in order to get the correct pathway for this to occur. So
I haven't seen it.
But it's true in the wild type, and then he disrupts that when he makes the mutant. So I'm wondering, I wonder if you could say something about that.
Sure. So my comment would be, in the calculations Jose described, he's sampling the geometry of the protein and at snapshots computing the coupling. So what Tom Miller pointed out was there are some relatively large-scale fluctuations in the hydrogen bonding contacts that you need to include when you calculate the tunneling matrix elements. So they're part of the ensemble. If there are fluctuations that either create strong pathways or shorten distances, they have to go into either the pathway calculation or the quantum chemistry.
Okay,
so Tom captured those by including a semi-classical treatment of the nuclear motion of the protein. It is very interesting. Yeah.
Do the numbers change?
Numbers change because I think the distance shortens, but I can't remember if it's a pure distance or pathway.
It's a 2 angstrom shortening of the
So they're probably bring the
So-
two different chains. Okay, that's right. So you bring two different chains together, they should shorten.
So I think they open up a hydrogen bond, something like that, and it allows the
From
distance to shorten by a few angstroms. So it should cause an order of
Should have-
magnitude effect. Yeah.
So in these plots, a ln K versus R, what would that mean?
That would mean that base couplings like that, you shorten by a large amount. Right? But the question is that, and in some cases, if you shorten one particular distance, then you're going even strengthen the situation of having a dominant pathway. So the question is basically if the short is one of these 3 space jumps that you have. Because the thing here is we don't have time to go about what's the difference about going through a single strand, what happens you have to jump between one strand to another strand, and that's probably what is changing by this hydrogen bond. That's a big jump. That's the biggest cost of this rate when you have this here.
At the end of the day, you need structure, right,
Yeah.
to make sense of this.
Any more? Yeah.
This is a more general question on the details. At the end of your talk, you said, if this is there, I don't believe it's there just as a random issue, but biology has to use it. Did I understand correctly?
Yes, what I'm trying to say is on the electron transfers that have to be fast, that happens on photosynthesis, that happens on our system, then biology really utilize quantum mechanics and try to get this dominant path for tunneling and do a situation like that. And do a situation where you avoid to have any sort of decoherence or stuff like that. So that's the case when you see between the phyllophyton and the first quinon. That rate has to be fast, otherwise don't have the charge separation. So these systems, you do the calculation, and you observe they're very robust. They have a couple paths that dominate, but they're coherent, interfering, and do the situation. You go to situations where the electron transfer doesn't have to be optimized. Biology doesn't optimize that electron transfer to make sure you have a single tunneling path dominate the situation because there's no reason for it. The system is fluctuating all the time to a larger amount, and it's not a problem with quinons because that's a case where the electron transfer is not a rate-determined step. It's mostly the gating process that's determining that reaction. So that's a case you don't have. So there are few effects what observed in biology really deals with the quantum mechanics, the case optimize the electron transfer when you really need to do it. But if you don't need it, there's no reason to evolutionary try to select it for good paths.
I think maybe we'll move on to David Barrington now, and then we'll have a more general discussion here. Thanks a lot.